Um,
There we go. Yeah, so an atmosphere is literally the average um, pressure at sea level across the Earth. And that's like equal to like 101, 101.35, something like that. Pascals. A bar is just like a more idealized version of that, which is just 100,000 flat pascals. So they're very similar atmospheres and bars. Again, if we're like dealing with earthly measurements, we will probably use atmospheres. And if we want just like something cleaner, we'll use bars instead. But they're very close.
okay. We can use bars.
What's
Yeah,
a torr again? Like torrs?
yeah. TORR, Tor.
Yes.
That is what we call the millimeter of
TORR?
mercury. mmHg is a millimeter of mercury. Um, and so I know it's strange, like we're using millimeters to measure pressure, but it's about the change in mercury, the length, the dimensions, how mercury changes with differing pressure. And so we get that different changing depends on how much pressure we apply to mercury. Remember, mercury is liquid, and so it is incompressible. And so it does change shape and dimension when we put it under pressure. And so a torr is just 1 millimeter of mercury. That's probably the least common that you'll encounter. It's probably mostly going to be pascals, bars, or I don't know, PSI because we're in the US. But yeah, those are units. Aiden, you were mentioning Pascal's principle.
Uh,
Uh, what was Pascal's principle?
P subscript 1 equals P subscript 2. I forgot how to say that, but
Yeah, I mean that's fine. You can just say P1 equals P2 or P sub 1 equals P sub 2.
okay.
Um, but again, remember that subscript is just our notation for what happened first and what happened later. So our pressure at one point in time will be equal to the pressure at a later point in time. And so why is that important for us? And remember,
Yeah, I don't remember.
Tommy, why is it useful that pressure would remain constant through a fluid?
Uh,
Sorry,
it's
not time. Yep.
what?
Sorry, no, nothing. Keep going.
Uh, so that it's like, so that you don't have like to like calculate like the high and low.
Thinking more like a real world application here.
And
Um,
Is it for like
so
hydraulics or something?
it's easier to calculate.
yeah, yeah, hydraulics. Very good. Well, I mean, yes, it is easier to calculate. It's, nice and simple. But hydraulics is the main application of Pascal's principle. Again, so if pressure is constant, what does that mean, right? That means that force over area must be constant, right?
Mm-hmm.
Okay, let me just pull up the thing from last time. Hold up, guys.
Hmm?
Right. So if pressure is constant, then that means force over area must be constant too, right?
Mm-hmm.
Um, sorry. But right. So let's say we can only apply so much force at once, right? Because humans were physically limited in how much force we can apply. So we can only apply this force. The key
Or
thing
also
is,
like arms.
yeah, yeah. Um, the key thing is if we apply that force over a really small area, then we have a really big pressure.
Mhm.
And then what we can do is we can increase our area at another place. And because the pressure at this point in the fluid must be the same as the pressure in this point of the fluid, then the force here must also increase because the area is increasing. And so we're going to get a lot bigger force out of here from even though we only put in a little bit of force.
I
So we're
thought
just
it's like,
It's kind
utilizing.
of like a water gun, right?
isn't it impossible to increase I mean I'm isn't it
Create
impossible to
energy, right?
create energy? Yeah, 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 that's why I was gonna
Yeah,
Technically, you're
okay.
not creating energy, but you're converting it or something.
You bring up actually a really great point. Um, and that's about the distance that these things travel, right? So,
Oh,
we
this is-
have conservation of energy, right? So what, we can talk about work, right? Work, how is work related to energy?
where
Work
is
energy theorem?
work
What
and
is
kinetic energy is
work uses
oh,
energy? Yeah, energy is the ability to do work. What does that mean? How is energy related to work? Kinetic energy, I guess. So
it's Kf equals Ki plus W. Is that one of them? I mean, that is one
yeah,
of them.
yeah. That's the work energy theorem, right? So the amount of work you do will change the amount of energy that something has, right?
Yeah.
And so what's our equation for work?
It's somewhere in here.
Take a second, you can find it.
I've work done by basically everything. And constant force and kinetic energy, yet I don't have the work thing.
It's related to force, specifically force times what? In the
Force
chat.
times weight.
Yeah, displacement, exactly.
So is it kind of like this?
看一下这个，看一下这个拿过来，看一下，
It's a little different here. Let me actually annotate this.
明白了啊？
Here we go. So here, notice that we're applying this force over an area, but we're doing some work, right? Because as this goes down, that's some distance d, right? I have to
Mhm.
push it down some distance d, right?
Yeah.
And so the caveat with Pascal's principle is that I'm applying some force for some distance d, right? And so I'm doing some work w here at this end, right? Now, let's say that this were to go up the same distance d. Oh no, what did I do? Sorry. Let's say that this goes up this. Oh no. Sorry, guys, I'm really bad at drawing this. Ah. All right, here we go. If this goes up the same distance d, then I applied a bigger force over the same distance, so would my work be bigger or smaller, or the same? Same force, or bigger force, same distance.
I think it will
Sorry, work, I'm just writing it here.
oh
Force times displacement. Sorry, again, for the crude handwriting.
force
So if I increase my force, but keep my distance the same, will my work increase or decrease?
increase.
Right. And so remember how work is related to energy, right? Well, that seems like we are creating some energy where we're putting in we're doing some work here. We're getting a lot more work out this end, right? So how do you guys think that we can rectify this so that we're not actually creating any energy? If our force is going up, what must our distance do?
Go up. Oh, go down.
Go down. Right there. Because if our distance goes down, then by the same amount, then it cancels out, and we have the same work being done. And so the caveat with these hydraulic systems is that you can't actually go the same distance d. Oh, there's Arjun.
Wait, he's here? Oh.
Yeah. Hi, Arjun. So the caveat is that you can't actually go the same distance. Because that would be creating energy. And so yes, you can get a lot more work, so we can lift heavy things like cars and like large machinery using these hydraulic systems, but we can't lift them as far as we can push down like here, which is the main drawback. But we can lift them a lot easier than we could with our hands.
Wait, isn't that what they
use.
use in excavators or something? Like they just push down on one side of the hydraulic thing, and then the water.
Excavators,
Yeah,
like
like the water.
archaeology.
I mean, like the one in construction sites.
Oh, that kind of excavate. Sorry.
If this like really works, then why don't they use this for like almost everything?
Well, they give me a thing where you think this can be used and isn't.
Elevators.
Is it used in elevators? I have zero.
As far as I
Like
know, it
chains
is.
and motors or
I'm
something.
gonna search it up.
Yeah, as far as I know, it's about the gear ratios, and they have full motors on the elevator.
Yeah, gear ratios all also.
I think
But
the
think
only
about-
reason why I know that is because I watched brake signs or something.
But think about it, like if we were to put a hydraulic in there, how big is the distance between like the top floor and the bottom floor of an elevator?
It's gonna be really high up, and
Yeah.
I'm pretty sure the water won't even get there.
So yeah, it's a pretty big distance, right? Think about it here. We need to apply a bigger distance we need to push down just to get this force to go a little distance. So we need to push down a lot, like a very large distance, just to get this elevator to go up, like even a couple floors, right? And so it's not really practical to use it there. I'm sure it can be used, but
Yeah, it's gonna
I think
be really expensive and not go up as high as what a chain / gear ratio and motor would
I
go.
guess it would probably work with other stuff better.
yeah, I mean I think we use it pretty commonly in what it's good for, you know.
I'm
We
gonna
would-
think of more ways to use that.
All right, it's a good challenge. Where should we be using this that we aren't? You know, I mean, to lift heavy stuff on the regular.
A staircase that grows automatically when you step on the first step. Well, I think
That is something
could
you
be.
need.
All
That
right.
could happen.
Are we clear on this part with the work? Why we can't go as high?
Yeah.
No, I just joy.
Oh, okay. So quick recap, Arjun, for you. We have Pascal's principle. You remember this, right?
Pressure on one point is equal to a pressure on another point as long as they're interconnected, something like that.
Yeah. By this fluid, right? And so if we have small force, small area, we can get big force, big area over here, right? But main notice here that we're putting down some force, and this has to go down a distance d, right?
Mm-hmm.
And so we're doing some amount of work to push down the fluid, right?
Mm-hmm.
Now let's say we get a much larger force and we go up the same distance d. We're gonna have created work, right? We're creating energy, right?
Yeah.
Which is why we can't actually go that far up what with these hydraulic systems, right? So this will only go up a little bit, but it'll be a lot easier to pull it, but it won't go up as far. So we need to push it down a lot, a great distance to get the work required to push it up.
That makes sense.
Yep, it's just the gist of it. So we're all clear with Pascal's principle, this idea of work and how it's related here.
Yeah.
Okay, cool. Sorry, just gonna clear that. Yeah, so fluids, pressure, Pascal's principle, went over all this. What do you guys remember about density? Well, I guess it's kind of already told you here. Let me stop sharing for now. What do you guys remember about density?
It's
G equals M over V.
rho.
Yeah, those were all the things you just saw. So yeah, we use the Greek letter rho for it. What does rho look like?
A P.
A P.
Yes. It's pronounced R in like Attic Greek, but yeah, it looks like a P. So we use rho, and what is density?
How tightly packed something is. And
Right, what's our equation to show how tightly packed something is?
G equals M over V.
Right. Again, that picture used D. I would suggest using rho instead of D, just to be more technical.
I'm
Wait.
pretty sure we learned density in 6th grade. Apparently,
Density feels really similar to like a pressure.
oh
Yeah,
yeah,
they are related, which you'll see in a second. Yeah, I think density is one of the things you do in early middle school. I don't fully remember, long ago. But I'm saying you guys should all be pretty familiar with the density, at least. Do you guys remember what the density of water is?
I don't. It's 1 gram per square inch, right?
What's your units of density?
Um, grams.
It's one part of it. Remember, you can just plug it into the equation. So mass over volume. Our unit for mass is grams, like you said. What's our unit for volume?
Volume is
Or let's say have a cube. What's the formula for the volume of that cube?
um length times width times height.
Right. What's the units of length?
Meters,
Unit of width?
meters,
Unit of height?
meters. So it's
So you
meters
multiply them.
cubed.
Exactly. So we have like, I guess I never actually introduced. We have like two metric systems. We have like the CGS and the MKS system. What do you guys think those stand for?
Microcores.
No.
Oh,
Like my units, remember, what do you think?
Centimeter, gram, second,
Yep.
meter,
Uh,
kilogram, second.
Yep, there you go. Those are our two. So it's just like whether we prefer to use the larger ones or the smaller ones. We will always prefer to use MKS. CGS is very stupid. Um, like the unit of
Yeah.
force in CGS is called a dyne. Like who knows or cares about that?
Nobody.
Exactly. Why
a
not just use
dyne.
yes. Why not just use newtons? It's so terrible.
They
You
are
know,
built different in a bad way.
the unit of force in the imperial system is called a slug.
What?
Like a what? Yeah,
Oh,
it's literally called a slug. Like
I'll take 10 slugs. Yo, these people are buying
it's
10
so awful,
slugs.
anything but MKS. Anyways, so yes, we can use grams per centimeter cubed, in which case it's equal to 1, the density of water, or we can use kilograms per meter cubed, in which case it's equal to 1,000. Um, so yeah, so one gram per centimeter cubed. Remember, it's important because our dimensions, so volume, so cubed, or 1 kilogram per meter cubed.
Why is it so spicy? Oh, never mind.
Yep. So that's density. You guys all got that pretty easily. And remember that thing for water isn't just a coincidence. It's literally how we defined what a gram was. And so we kind of just set it up that way. Anyways, moving on. So how do we think that pressure is related to density? We have an equation that relates the two. Remember what it is?
Oh,
I couldn't quite catch that.
Right. So we have an equation relating pressure and density. Do you remember what that equation is?
Oh, no.
Good. Good. Tommy, you remember?
oh, oh. On my notes, I have an equation written as P equals P0 plus PGH. Does that have anything to do with it?
That is the equation I'm looking for, but read that again. Make sure
I can't find
you
my
messed up
notes.
something there.
It should be row. Like,
Pressure.
you have to say
Oh,
row.
There you go.
ah,
It's rho GH. So here we go. Another equation for pressure.
Oh, wait, I have that in my book.
P equals
Oh, I
P naught
never
plus
knew.
rho GH, right? So remember rho is density here. And so this is how we're relating our density to our pressure, right? The
Can we just
denser,
call it little p and then pressure big P?
no, because those are two different things.
Okay. Like pressure
Um,
is a uppercase P for this one, and rho looks like a
but
lowercase p.
it's not a P, it's a rho.
I mean
Two
rho.
separate things. Because remember, what do we use little p for?
Uh, something.
Right.
Yes.
What is that something? We remember we talked about it in like half an hour ago. You got confused with them.
Momentum.
Oh
Yep.
yeah.
Ooh.
Right. So we use little p for momentum. So we use rho for density. And so here, obviously, so if a fluid has a higher density, then it's going to have a higher pressure at whatever point, and again, it's proportional to its acceleration. And this h is just how high within the fluid, how much. Because remember, if we have a lot of fluid on top of it, it's going to be, there's more things weighing down, there's going to be higher pressure. And so the deeper you get, the greater your h becomes, the higher your pressure will be. Do any of you remember what P naught is?
Oh yeah, P naught.
When
Um,
pressure is 0.
It's the initial pressure.
Initial pressure, specifically, what is it? Not quite initial pressure, but like every point on Earth will have at least this pressure. What is that pressure?
Universal pressure.
atmospheric.
Yes, atmospheric
Oh.
pressure. Good job, Tommy. Right, so remember every place on Earth will have at least atmospheric pressure because the air above us is weighing down on us. And so in this equation, we just make sure that, like, let's say I have a point right here. Yes, I have this column of water pushing down on me, but I also have the entire atmosphere above it also pushing down. So I have this P naught, the atmospheric pressure pushing down, plus the pressure from the water above it, this rho GH. You get some intermediate pressure out here. Right. That's pressure. Any questions about that?
Never mind.
I mean, do you have one? Ask it if you do.
No.
Oh, okay. Anyone else? This makes sense? Okay, then.
Yeah.
I'm gonna move on. This next thing is gonna be a little complicated. It's gonna be a really long formula. Don't get too scared.
Uh-oh.
My brain. feels-
Wait, no, not yet. Sorry.
Oh.
You guys remember buoyant force? Not yet. Sorry. But we talked about Archimedes' principle, right?
It's not too long.
Not
No,
that.
no, no. This isn't the long one. Sorry, I thought we were getting to Bernoulli's, but this is Archimedes.
How
This is
long
what
is
you
it?
guys
Of course, there's an
already.
equation for Archimedes' principle.
There is an equation. I know you guys all know it from like elementary school or whatever. Where like if something's less dense, it'll float, right?
Yes.
The reason for that is this, right? If something's less dense, it'll float. This is our equation for buoyant force. So you know how like if you're in water, you feel lighter? Like it's really easy to carry things underwater, right?
Yeah.
Well, that's because of buoyant force, Archimedes' principle. Uh, sorry. Yes. So think about like something here, right? Can of beans. Is the pressure at this point going to be? Oh, I guess it already tells you in the picture. But think about it, right? Pressure is proportional to the height above the point, right? The amount of water above it. So at this point in the can of beans, we have only this much water pressing down. But at this point in the can of beans, we have a lot more pressure pushing down on it, right?
Yeah.
Now if the water is pressing on, if yeah, so the water here, there's greater pressure down here. And so because this is greater pressure, there is actually a net force upwards because that this thing has volume. Does that make sense? Because the pressure at the top will be less than the pressure at the bottom. So the pressure at the bottom is going to push it up.
So if I put a rock under the water,
Mhm.
oh wait, yeah, since a can of beans is a lot bigger, like, and it has a lot more volume than the rock. Like if I put, for example, a big rock,
Yep.
like hold on, since it goes up to like here, let's just say here, and
Yep.
then the rock goes all the way down here. Since there's
Mhm.
since there's basically this is a weaker pressure, and this is greater pressure. Will it just go up and then fall back down? Like,
It's a great question. So that weaker and greater pressure rate leads to a net force. Sorry.
hold on,
And
let
that's
me
this
Google.
force, buoyant force, right? Now it's
Mhm.
not directly, it's pushing up, but what's pulling down on the rock or the can of beans?
Gravity?
Exactly, gravity. And so you have two forces at play. So the buoyant force is trying to push against the gravity. Now the thing is, the buoyant force will only outweigh gravity. The buoyant force will be stronger than gravity if the density of the object is less than that of water. That's Archimedes' principle,
Oh, okay.
right? So this force is going to be stronger than gravity if this is actually the density of water in this equation here. But if the density of the object is less than the density of the water, then this upwards pressure is going to be stronger than the force of gravity pulling it down.
Mhm.
And so in that case, that's why things float, because they will be pushed to the top instead of gravity pulling them down to the bottom. But in most scenarios where the density is greater, then it will be pulled down. You had a great insight too about the size of the rock. A small rock won't have that much buoyant force because it has a small volume. A
Mhm.
larger rock will have a larger volume, and so it'll have a stronger buoyant force.
Yeah.
Realizing that we're kind of out of time now, so I'm going to stop there with Archimedes' principle. Any questions about what we've gone over?
No. Wait,
No.
just a
Yep.
quick question.
Yep.
Are we going to go 15 minutes over because there's no bio today? I don't know about any other schedules. So
No, we
Oh,
will
there
be
isn't bio
ending now.
today?
I'm pretty sure
No,
no.
there is no bio today. But we will
Oh.
have to end like now once this meeting ends. So get in your questions before it does.
Okay.
Any questions? No. All right. Email me if you do, of course. In that case, you guys are all free to go. We'll get to the long equation next week.
Okay.
Yep. Thank you guys.
Thank you.
Yep.
Bye.
Bye.
Bye.